Yeah.
All right, well, we were in the middle of a proof last time, and I've been thinking about some questions that we had during and after the proof, and I have a couple of comments I want to make that might clear up some things. First of all, there are many different variations of a red-black tree. And so the first comment is, this proof that we're giving is an upper bound for the performance of a general red-black tree. Okay? So we're not making any assumptions in this proof about left-leaning. So what we're saying then is that what that means then is that in this general proof, you can have a link, you can have a right link as well as a left link be red. Okay, so is everybody clear on that? Actually, I should maybe, let me just mention this. There is, Sedgwick defines there's more than one left-leaning red-black tree. Strictly speaking, the left-leaning red-black tree that we are using in our project is called a 2-3 bottom-up red-black tree. And there's another one that is slightly less restrictive. It's called a 2-3-4 top-down red-black tree. Okay, and you know, he goes into infinite detail about all the ins and outs of these things. But the simplest one, and the one that we're going to do, is we're doing the 2-3 bottom-up red-black tree. But in general, there's just you have just red-black trees. Okay, so anyway, point being, for our purposes here, is that this proof on a lower bound, on an upper bound of the performance is we're proving a big O, is that this is for red-black trees. So we don't assume anything about the left-leaning, or, you know, we don't this proof doesn't have these additional restrictions about left-leaning. All right, so that's one point I wanted to make. Now here's another one. This particular step right here, the minimum occurs when links to L and R are black, is, I had a hard time explaining that last time, but I think I can show this to you with a picture. Because look at what we're trying to do here in this induction case. We must prove that, what we're trying to prove is that n, x comma h. Now what is that n? That's the number of what? Internal nodes. Yes, that's the number of internal. So we're making a statement about it. We are relating the number of internal nodes to the what? What's that relating? What is that to? What is that to? What is that BH? We are relating the internal nodes to the what? To the black height of the tree. And the black height of the tree is in turn has a limit on the total height. So basically what we're doing is ultimately we will have a relationship between the number of nodes and the height of the tree. And the height of the tree is what determines the performance. Are you with me on that? So in general, what we want to do is we want to have this bound. We want to have this bound. And this step right here in the middle, it says the minimum occurs when links to L and R are black. I think the way to see this is like this. Let's go back to our tree. Let's go back to this tree that we started with. This figure right here. Now look, you guys, you see this is the tree rooted at 60. Now do you see the link to the right is a black link, and the link to the left has a what? Rooted at 60, the link to the right is what? Black, and the link to the left is what? Red. So do you see, by virtue of the fact that the link to the left is red, you can have more nodes. You see, if it's to the right, the minimum occurs when the link is black. I think maybe just that visual can explain that step. You see, because if it's red, then because you've got more chances to go down to maintain the black height of the tree, because you know you don't count the red links when you do the black height of a tree. Does everybody see? So that's how that step works. That's the justification for that one step. All right? And so at the end of class last time, we went ahead and got all the way down to the end of this induction case. And so basically what we did is we proved, well, here, let's go back and write what we proved. So here's the lemma. The lemma is that n sub x comma h is greater than or equal to 2 the back height of x minus 1. And that's the key to the proof. So all those steps are important. So now it's just, the rest is trivial. We have two more lemmas, one more lemma, and then our final result. So this lemma 3 just comes from the two previous lemmas. Look, what does it say? It says n of x comma h is greater than or equal to 2 to the h over 2 minus 1. Well, look, we just did. We'll start with n of x comma h. Right, so that's the number of nodes that's the number of internal nodes of a tree rooted at x with height h, and this is greater than or equal to, by lemma 2 that we just did, what? Greater than or equal to what? Right. Yeah. 2 the bh of x minus 1, right? But we saw that this double, what did we see about the double? No one is greater than or equal to the, no path from the root to the bottom can be greater than what? Twice the height of the shortest one. Is that right? That was lemma 1. So this is greater than or equal to, by lemma 1, what? Wait, lemma 1 says what?
The black height is greater.
The black height is greater than or equal to h over 2. So therefore, by lemma 1, that is greater than or equal to 2 to the h over 2 minus 1. Are we good? Okay. But look, you guys, that's the red-black tree height bound. A red-black tree with n internal nodes has height h greater than less than or equal to 2 log. So now all you got to do is do a little math, right? Solving is all we got to do is just take this, starting with lemma 3. We just start with this result from lemma 3 because we want to get h. The performance is related to h, right? Well, we're even going to do simpler math. We're just going to take one to the other side, right? Now what will we do? Now take log base 2 of both sides. And by monotonicity of the log, that's h over 2 is less than or equal to log n plus 1. And then what do we get? Multiply both sides by 2 and what? H is less than or equal to 2 log n plus 1. Are we good? Does everybody see? Now look what we have proved. We have proved because the performance, whenever you do a contains, it's a binary search tree, so the number of decisions in a contains is the what? Is the height of the tree. And whenever you do an insert, the worst case doing an insert is it gets inserted at the bottom, so that's the height of the tree. Is everybody clear? So basically, what does this show? What we've proved then, our result is that the performance, whether it is a contains or an insert, and also if you delete, you delete from, you find the one to delete. That's the height bounded by the height of the tree. So basically, what we're saying is that the performance of a red-black tree is big O of what? 2 log n plus 1. Is big O of 2 log n plus 1. And so basically that's the same as what? Big O of the 2 and then the plus 1, it's what? It's big O of what? Log n. Does everybody see? So that's what we've proved. Now here's the thing. There was an interesting question that came up the other day about do the constants ever matter? And remember we said that, and this is a general principle, if you have two algorithms that have the same big O, or the same big theta, then it's not that they may not have equal performance, because if they have the same asymptotic behavior, then the better one is the one that does have the lower constant. Are you with me? And here's an interesting fact. Remember we said that there were different kinds of height balance trees. And do you remember what AVL stands for? Those three guys. Yeah, it'd be hard to remember their names. Adelson, Velsky, and Landis. But anyway. The AVL, for comparison, the height balanced AVL trees have H, you can prove it has H less than or equal to, look, 1.44 log n plus 2 minus 0.33. So you can actually, if you go and learn that algorithm and then analyze that algorithm, and there's proofs, you can, you know, all this is part of the data structures literature and well-known results. You can Google this stuff and find all this stuff on Wikipedia. But anyway, so what is this? So what this 1.44 for AVL trees is compared to what for the red-black tree? 2. 2. You see. So those trees have better. They are shallower. They are shallower, but it takes more computing to keep them shallow. Okay, so they have slower insertion and removal because it takes a lot more. It takes more computing to insert and remove, but all that extra computing buys you some little shallower thing. But that's still big theta or big O of log n. All right, so these balanced trees. Okay, now we get to do some code. See how these things actually get built. So the implementation of the LLRB tree, the left-leaning red-black tree. Okay, and we already did the demo, so now check it out here. Again, we have two classes. We have a class for the tree, and then we have a class for the node. All right? So here's the class for the tree. And by the way, our implementation here is not going to be any fancy schmancy composite, you know, visitor, none of all that stuff. This is straight old, plain up, raw pointers. So this is more like the by tree L. Okay, so we're going back to basics here. So what attribute does a tree have? What's the name of the attribute for the tree? Underscore root. And what is it? A what to a what? A pointer to a node. All right. Oh, and by the way, this is node T. It's not K, comma, V. So typically what happens is these trees are typically used to implement dictionaries. So this is just a simplification. All right. So we're not doing the key value pair, but we could, and maybe we should. But you know, we want to concentrate on the algorithms for insertion and deletion and not have all that key value pair get in the way. So this is a simplification. Is everybody clear? And by the way, this is the way we're going to do it for all of these balanced trees. They all are used for dictionaries, but we're going to simplify. We just don't want to have that key value pair to complicate up our code when we're learning this stuff. All right, so the tree has a constructor, and look at the post condition for the constructor. This left-leaning red-black tree is initialized to be empty to test the algorithm, and then there's the toStream.
Now that we are using shared pointers, we do not need to actually write the constructor, because with shared pointers there is a feature that when they are initialized, they are automatically initialized to the null pointer. And so therefore when we instantiate a new LLRB tree, left-leaning red-black tree, the underscore root will be automatically initialized to the null pointer, and therefore the red-black tree will be initialized to be the empty tree. So here are the methods that for a dictionary that the usual ones. We have contains, which returns a Boolean, returns true if this tree contains data. We have insert with the post condition that data is stored in this tree in order and with no duplicates. So even though we are simplifying this project by not having the key value pair and only storing the key value, we will still maintain the insertion to do nothing when if there is a duplicate already in the tree, and of course there is no value to set like there would be if we had a key value pair. Then the usual remove, which is the post condition: if data is found, then it is removed from this tree. And here again, the remove for a dictionary would return the value that got removed, but here again, since we're not using the key value pair, it's just a simple void remove. This is to keep the code simple. And then we have the usual toStream.
Right. And so now comes the methods for a node. So, by the way, I haven't really displayed this as frequently as I could have. Have we talked about what it means to what a friend class is? Okay, we know that. So that's access. You have access to the private parts of the other class. So anyway, now check it out, you guys. What are the attributes of a node? What does it have? Underscore left, which is a what to a what? Pointer to a node. Underscore data, which is a what? Data of type T. Sorry, underscore data, which is of type T. So that's our data part. And then an underscore right, which is a pointer to a node. And now, you guys, look what we have. Underscore color, which is a Boolean. Now, why do you suppose underscore color is a Boolean?
Because you're only going to have two values.
You're only going to have two values.
Probably easier for
the code. Yeah, the code. Yeah, it's interesting. This is Sedgwick's idea.
So did you make red true?
Yes, you will see that coming up. Yeah. So now we have the constructor and the destructor for nodes. Oh, now, and this is important item for the constructor for a node. What's the post condition? This node is allocated with underscore data set to data. And what about the color?
Set to red.
That is set to red. Now that's going to be important. Why do you suppose it's going to be set to red? Because we want to maintain the what height? What is what's one of the key value, one of the key concepts that we have to maintain? The black height. And so if you stick in a node with a red link to it, you are not doing what? You're not changing the black height, and so therefore it makes it safe to do that. Are you with me? Now these are all really important concepts. Okay? So, and then left and right are set to the null pointer. Now, I haven't, at this stage, I went ahead and stripped off the documentation for all these, and I'll show the documentation as we talk about each individual one. But these methods are all the methods of a node, and these are all private, and these are all used by the project to implement those properties, those methods of the binary tree. So one of the most important ones is called fix up. We'll see how this is. It's kind of complicated, but we'll see. There's fix up. There's flip colors. Now the insert is the node version of the insert, of the list insert. Okay, and then check it out. What's the next one? Here's your question. Here's your point. Is red. It turns Boolean. Okay, and then oh, and min. This is one you're going to write. We'll see this in another day or two, how min works. And then there's a move red left and a move red right. Those are used for deletion, so we won't need to learn those right away. We'll learn those in a couple of days. And then a remove is the node version of the remove for the binary tree. And then remove min is an internal one. And now these two we're going to learn in a minute. Rotate left and rotate right, and then toStream. And toStream, again, we saw that demoed, and we don't have that. This is the node version of it. And you won't have to mess with implementing that. And this next slide is a repeat of some of that code. And look what we have up at the top. Const bool red equals true. Const bool black equals false. So does everybody, you know what a constant is? It's like a variable, but value can't change. Okay? So that's for programming clarity.
What's the...
That is so the question is, what is the efficiency, or how does this work, a constant versus a variable? That's a really good point, and the answer is yes, and the other answer is you learn all about this in computer systems. how to access that. What's the difference between a constant and a variable at a lower level of abstraction, at the assembly level? Yeah, that's a really good question, and that's precisely one of the things that we just learn all about. So take that course if you can. So that's, and now here is a diagram of the structure of a node. So it has underscore color, underscore data, underscore left, and underscore right. So that's just a picture of the node. And typically, you know, there's going to be some pointer. The pointer is usually called H. You know, we kind of always use H as the pointer to a node. And look at is red. Now check this out. Somebody asked the other day, what about those nils? Are those actual nodes? And I said, well, actually, in the implementation, they are conceptually they are nodes, and they are black. And I've seen some implementations, they will actually put a node there, a black node there. You see what I'm saying? They would actually put a black node with no data, with, you know, with the color being black. But look how clever this is. Those are going to be nil pointers. So what does the code isRed do? It returns false if H equals null pointer. Otherwise it returns true if the H node is red. So look, what does it say? It says Boolean node, : is red, and what is H? A what to a what?
Pointer to a node.
A pointer to a node. Are you with me? So what does it do? It returns what? H equals. If H equals the what? The null pointer, then what? It returns black. See? So look, so even though there's not a node there with a color, it guards the fact that it's the null pointer. You see what I'm saying? So if it's no, otherwise, what does it now? And also, this is, if it's not the null pointer, then what does it do? If it's not the null pointer, we know it's pointing to a what? Pointing to a node. So then, what does it do? Returns H arrow color. Yeah.
What's the advantage of creating a constant variable red and black instead of just putting false or true?
That is a good question, and the answer is readability.
Oh, okay.
Code that this is internal code. You always want to have self-documenting code is really an important point in software engineering, software design. You want to have your code internally documented by having meaningful names, having for both constants and variables and methods. Yeah. So yeah. So everybody, that was a good question. Is everybody clear now on how this works and how isRed works? Even though there's not a node there, we're going to, when we analyze the algorithms, we're going to think about it as a node being there. And the color will be black because when we call the isRed, it'll tell us it's black, even though there's really not a node there. But it will be as if there's a node there with black link. So here's a picture of what the constructor does. Here's the code for the constructor. So notice the constructor for the tree, it just does underscore root, gets null pointer because it's the empty tree. Are you with me? And then what about the constructor for a node? So look what the constructor for a node does. So we give the constructor data, and then what does it do? It sets what? Underscore color to red, underscore data to data, underscore left to null pointer, underscore right to null pointer, and there's a picture. So this is, if you give it 50, you say I want a node with 50. The link is red, nil, nil. Yeah.
How do you know that the link is red? Because you're not trying to increase the black height?
Because, yeah, when do you want a new node? You want a new node when you insert. Where do you insert? You insert as a leaf.
Right.
So if you insert it as a leaf, if the parent node, if the parent link is red, you are not damaging The black height. Now that is super important. You remember how we counted the black height and we skipped the red links when we counted the black height. So you are maintaining the black height. You see, that's an invariant that you maintain. Yeah.
So you only find out if a link is red after you've checked the child. The parent has no idea what color link it has with its children.
That is true. You can't tell. That's right. What the link that you can test is the link to the parent. In any node, because the link to the parent is the color that is stored at the node. Yeah. So if you're up there, you can't tell what your link down there is. That's a good point. And what's really cool about Sedgwick, this code, is that before you had a link to the down and a link to the parent so that you could do stuff like that, but it turns out you don't need to do that. And so this is much simpler. This code is amazing. Okay, so now we have to learn some operations. First operation, there's going to be 3 operations that we have to learn in order to have all this stuff work. The first one is called rotate left. All right? Now look at how rotate left works. What we have before a rotate left is we have a situation where H is a pointer to a node that is rooted, and that is the root node 50, and it has a red link to the right of 60, and now these triangles represent subtrees. Hold on. Represent subtrees, and you see all the values that are in the left subtree of 50 are less than 50. All the values that are the left subtree of 60 are less than 50, greater than 50 but less than 60, and all the ones that are to the right of 60 are greater than 60. So you see then that this is ordered. Right? This is ordered. And furthermore, that link coming down from 50 to 60, we're going to assume that that's red, because you only do a rotate left operation if the right link is red. Now, so obviously with left-leaning red-black trees, this situation could not appear in a finished red-black tree, but in an intermediate situation, it could be there. And so what we have to do is we have to fix it up. This is one way to fix it up. Was that your question? Yeah. Good observation. Okay, so now look at what look at what this rotate left operation does. What it does, now look, you guys, it rotates left. So look, you want to see this? Okay, left. So look, the 60 goes up, the 50 becomes the what? The left child of 60, which is okay because we know 60 is greater than 50 because it was to the right before the rotate. Are you with me? And furthermore, what happens is the right child of 60 consists of all those elements in the subtree that are greater than 60, so it remains the right child of 60. But what about the left child of 60? Those are the ones between 50 and 60, right? So that becomes the what? The right child of 50. Now, do you see that that maintains the order? Are you with me? That maintains the order. Not only does it maintain the order, but look at this. The black height is maintained. Now, what do we mean by that? Now, this is an important point. What do we mean by the fact that the black height is maintained? Remember, as you count down, what do you do? To count the black height, you count down and you skip the reds and you just count the blacks. So look, before, if you're coming down and you go to the right and then you go to the right again, how many black links were there? There was one black link. Well, do you see that still on the right, if you go down to the 60 and you go to the right, that's still 1. The black height is still 1. And do you see then also what happens before if you go down to the ones between 50 and 60? It's red and then black. So that's what? 1. So do you see that if you go afterwards, if you go to the 60 to the 50 and then down to the ones between 50 and 60, that's 1. And also what about the black height of the ones less than 50? If you go down here, that would be 1. But look, boom, boom, that's also 1. So does everybody see that the black height is, not only is the order maintained, but what else? The black height is maintained. Doing this left rotate doesn't change the black height. Is everybody clear on this? Okay, so the black height and the order are maintained. So here's the code. Let's look at the precondition. Precondition, H arrow right is red. Postcondition, H is rotated left, as I just say the words rotated left, and that picture was what it did. Now here's another thing, and this is a little tricky, you guys. We're going to use pointers in a way that we have not used them before. So we're going to have to get used to this. The postcondition is a pointer P to the root node of the modified tree is returned. These functions are going to return pointers. We haven't done this we haven't used this style of linked data structures before, where methods return pointers. So what happens is, because they return pointers, then the calling one assigns that pointer to something. Now this is a big idea. You're going to have to understand this to understand the code. Okay? So postcondition is a pointer P to the root node of the modified tree is returned. Notice what rotate left has. What does it do? It returns a what? A pointer to a node. And it's given a what? A pointer to a node. It's given a pointer to a node. It does something and it returns a pointer to a node. Are you with me? Okay? So look at what it does. And then the postcondition is P arrow left is red. So after the rotate, that link, the left link is red. So now let's take a look at what it does. I have a graphic here to show you each one of these statements. Node star P gets H arrow right. Can you visualize? Node star P gets H arrow right, so let's point to that one. And then what? H arrow right gets what? H arrow right gets P arrow left. Can you visualize? Well, we'll see in a minute. And then P arrow left gets H. Then P arrow color gets H arrow color, so we want to maintain the color of the node of the link that was coming up, that was coming in from the top. You see that's what that does, that maintains that color. And then H arrow color gets red, and then what does it do? Return P. So let's see if we can remember those. Okay, so check this out. So here's our initial tree. H is pointing to the 50, and so we assume that's the parameter, right? Are you with me? That's the parameter, and then there's 60, and okay, there's our initial tree. And that first statement was, do you remember what it was? P gets H arrow right. So now, does everybody see that? That makes P point to the same thing that what? H arrow right is pointing to, and H arrow, I'm not showing the structure of the, I mean, you guys, I don't have to show the boxes with the, right? Okay, is everybody clear? P gets H arrow right. And what was the next statement? Do you remember? Can you tell actually from here what has to happen? Look, can you tell what has to happen? I mean, knowing that this is going to go up like this, what's going to happen?
You make H right.
H arrow what?
Right.
Gets what?
P left.
Yeah, see? You see how I did it. Now, are we good? More pointers. I know how to work pointers. Okay? And what was the next one? Now what has to happen? Do you remember?
P left gets H.
P arrow left, sorry, yeah. P arrow left gets H. So that moves it up there. Are we good? Is everybody clear? Okay. And now I think this was your question. P arrow color gets H arrow color. So see, if the color coming down from H was black, then we want to duplicate H's. We don't want to change the color of that link coming down, because that would change the black height.
Aren't you not allowed to have two reds in a row?
Yeah, so these are intermediate.
It would never be red.
Well, actually that's a good question. It would never be red. The answer is it might be, and therefore need to be, it might be in the course of either inserting or removing, and therefore would have to be fixed up. Okay. So these intermediates, it's the same question that Xander had, you know. So yes, right. So what we do, so the code makes sure that the rules are followed in the end. Okay. Yeah. All right, is everybody good? And now, what was there? One more?
H gets red.
H gets red. And furthermore, what is P pointing to? This, and what gets returned? P. So a pointer to the rotated one
The new top one.
Yeah, the new top one. That gets returned. That's important. That gets returned.
Okay, so it's just a shape that gets like rotated.
Yes, and the colors.
So shape and the colors get rotated, but like where the numbers are, that's not rotated, is that?
Well, those numbers, notice that no nodes are cut, there's no new, there's no delete, and there's no copying of any data. I don't know if that
Yeah,
helps.
I'm just saying like 50 and 60 technically, like 60 or 50 was the head at the beginning, and now 60 is like the head.
Yeah,
But it has to be.
but P, the post condition is that P points to the new, to the rotated one. And now what's going to be interesting is, we're going to have the one that calls it, we're going to have H gets rotate left. So that will be the new H. You see what I'm saying? So because it returns pointers, then we're going to these pointers get this rotation.
Yeah.
So you got to be, yeah, it's a little tricky. It's a little different way of thinking. Yeah.
I don't know if we're programming insert, but this is different. So you would.
We are programming insert.
Okay.
Well, I mean, this is used in insert.
Yep.
You're going to program parts of it.
Of insert for homework, right?
Well, the actual code, all the code for insert is complicated, and that's given. But these are parts,
Okay.
insert calls these.
Yeah.
We'll see it in a minute.
Okay.
We'll see it in a minute. Okay, so now, not only do we have a rotate left, we also have a rotate right that gets used in these intermediate steps. And what does it do? Look, before rotate right, it's, now instead of left, it's what? Okay, rotate right, and it does this. And guess what? First of all, the black height and the order are maintained, right? Because it's just the opposite. And furthermore, exercise for the student.
If it's a left leading tree, when would we need to rotate it right?
Yeah, that's here again. It's the same answer. It's all in these intermediate steps. In the intermediate steps of both inserting and removing, you can have a situation where that happens, and so these are operations that you do to fix it up so that it follows the rules in the end. Again, it's the same concept. Is everybody good? So you see how to do that? So that's your job. All right. Now there's one more. Here's another one, and you're also going to do part of this also. And don't ask me why. What are you going to ask me? Well, in part A, there's a red one to the right. Well, how can it be? Is it? Well, in an intermediate step, it might be. Okay, so this one is called flip colors. Okay, so flip colors, what happens? Before flip colors, we have, well, in this picture, we have a black one coming in, we have two red ones coming out. And after flip colors, what happens is they all get flipped. So look, the black height is maintained if H is black and H arrow left and H arrow right are both red. And in fact, that's when it gets called. It gets called under those conditions. Because all we want to do is flip them. Now look, this is really clever. How do you flip a color? I did the H arrow color. You can do the left and the right. All you have to do is what? H arrow color gets what? Not H arrow color, because colors are what? Booleans, and not false is true and not true is false. Not red is black and not black is red. So I did this one. You can do this one and this one. Is everybody clear on how to do that? Okay, that's pretty straightforward. And now comes a big deal. How do you insert into an LLRB tree? Now watch this. This is quite conceptual. This is very conceptual. So here we have, let's do a little code walkthrough. Here we have the code for inserting into a tree, and you notice the one at the top is the tree version. So this is void LLRB tree : insert, and what do we give it? Data, right? And so what happens is root. So what does the tree version do? What does it do? It says underscore root gets what? Underscore root arrow insert. So the tree version calls the what? The node version of insert. Now is everybody clear on that? And look at what it does. Underscore root happens 3 times in this statement. first of all, it's underscore root gets. Are you with me? And then it's underscore root arrow because that calls the node version of insert. Are you with me on that? And then it passes what? Underscore root. So you're saying, I want you to, so the node version has to be given a pointer to the node, to the root node to do the insertion. Are you with me? And then data. And then after it does that, it does all this and the fix up and blah, 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 blah. And then the very last thing it does is what? Root arrow color gets black. And it can clearly do that because if it's red, it doesn't matter, right? Are you with me? So because there is no parent, we don't count the parent. There's no parent of the root, so we make it black.
So
there's no parent of the root.
So
We just make it black.
So that doesn't count as one of the...
No, it never would anyway because there is no parent of the root.
there's technically no.
This is like the very first one.
But it doesn't...
Yeah, but there's something is stored there, so let's just make it black.
It has the underscore color.
Right, yes, it has the underscore color. Right, right, right.
Did it not already have a color?
Well, it did because the first time you put a node in, it gets put in as a root, and that color was red. The way you grow a tree the way you grow a tree when it starts off empty, it would be red.
Wait, before you fix it up?
Even after you well.
Because during the demo, I'm pretty sure the first thing you put in was in black.
I know. Well, the first thing I put in was a value, and it was black, and that's why.
Oh.
Because when we used the constructor, it was red, but now this made it black. That was a good observation, a good remembering from.
So, will it ever be switched back to red, the root?
No, well, it could be switched to red by virtue of the call to the node version. Well, because what it does is the node version returns a pointer to the node version returns a pointer to the tree with the node inserted, and that tree has been mutated. Mm-hmm. And the root after that might be red. That might have made the root red. That call might have made the root red. The link up from the root red. And so therefore we set it to black. By virtue of that call, it might have been changed to red.
The only time that you would want the root to be red is the very, very, very first time you ever put it in.
Well, yeah, but on the other hand, this will change it to black. So the root of the tree itself will always have a black pointer to its non-existent parent. Let me just run through this and give you some previews of coming attractions. Now this is really, this code right here, we have to get used to this feature of the code where all of these methods return pointers to nodes, and then so what they do is they change the structure that the node is pointing to, and then they return a pointer to the changed tree, and because it returns a pointer, that pointer gets assigned to something. You have to kind of understand that. So look at the code here. It's for the node version. Remember what happens is H is the formal parameter of the node version of insert. Are you with me? Okay? And so it starts off being root of the tree. If H equals null pointer, what do we return? New node T data. Are you with me? And so see the very first time, the very first time we call it, that first one, now can you see what happened? There was no recursive call. That returned one with a red, and then it did root arrow color gets black, and boom.
New data is the one that assigns red to something.
Yes, because it's a constructor, and we saw that the constructor always creates a node with a red link to the parent. Are we, because new executes when you call, constructor executes when you call new. Are you with me? Now look at this. If data is less than what? H arrow data, we just do what? H arrow left gets what?
Insert.
Gets insert left. H arrow left comma data. Do you see how that's working? Else if what? Data is greater than H arrow data. Are you with me? What happens? H arrow right gets. So now there's an H here, there's going to be an H here, there's going to be an H here, there's going to be an H here. As it goes down the tree, looking to where to insert, there's H's. There's these parameters. H's are being created all the way down the tree. All right? Else, what? We're not going to do anything because then they're equal, so there's nothing to duplicate. But now, by virtue of inserting that, what might have happened? We might have had what? 2 red links in a row. We might have had a link to the red link to the right. So what do we have to call?
Fix up.
And not only that, but what do? We return fix up H. And fix up, tomorrow we're going to learn the details of fix up.
The pointer to the fixed.
Yeah.
It has to return the pointer to it.
It has to, well, yeah, you see this sticks it in, this one sticks it in. Yeah. Ooh, this is, I tell you, Sedgwick's code is just, it's a gem. You will not appreciate how complicated this was before left-leaning. This is really good. This is kudos to Sedgwick. All right, good deal. See you tomorrow.